Hey everyone, welcome to Simplilearn's YouTube channel. In this session, we will be learning all the sorting and searching algorithms in one tutorial. But before we begin, let me tell you guys that we have daily updates on multiple technologies. So, if you're a tech geek in a continuous hunt for latest technological trends, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now without further ado, let's get started with the agenda for today's session. At first, we'll start with bubble sort algorithm. Followed by that, we have quick sort algorithm, binary search algorithm, insertion sort, linear search algorithm, BFS or breadth first search algorithm, depth first search algorithm, bucket sort algorithm, counting sort algorithm, and Radix sort algorithm. Followed by that, we have heap sort algorithm, merge sort, selection sort, shell sort algorithm. And finally, we'll wind up this session by learning greedy algorithm. So all these algorithms will be explained with detailed theory along with their practical implementation. I hope you will have a pleasant learning experience of all the searching and sorting algorithms in one tutorial. And if you require the code for all these algorithms, please feel free to let us know in the comment section below and we will be sending them off to you as soon as possible. Now without further ado, let's get started with the first algorithm. Over to our experts. Let's try to understand what is a bubble sort algorithm. The bubble sort algorithm is one of the fundamental and simplest forms of algorithm used to sort a collection of elements. The collection of elements can be either a set of numbers or characters. The control iterates through a sequence of numeric or character type elements in the bubble sort algorithm and rearranges them into ascending or descending order. The bubble sort algorithm rearranges one element at a time. The bubble sort algorithm is also known as the sinking algorithm. Here we have some random distributed elements which are 30, 10, 20, 50 and 40. And after performing the bubble sort algorithm, all the elements are sorted as 10, 20, 40 and 50. So how is it done? We will see in the next segment where we will understand the working terminologies of bubble sort algorithm. The bubble sort algorithm will not get implemented on the entire array in one go. Instead, it compares two adjacent pairs of elements in an array. If the elements are not in the correct order, then they are swapped, so the largest of the two moves towards the right. And this process continues until the most significant element or bubble is moved towards the highest position. After the first process is finished, the search for the next most significant object starts. And the swapping continues until the whole array is in correct order. This process is employed when you want to arrange the elements in ascending order. To understand the logic in a better way, let's go through an example. The example on my screen consists of 5 elements. According to the bubble sort algorithm logic, we need 4 iterations to sort all the elements in the ascending order or in descending order. The elements in the array are as follows. They are 3, 8, 4, 2 and 12. So in this array, the index begins with 0 and ends with 4. And each time, the bubble sort algorithm goes through the data element list and it is known as a pass. Let us analyze the total number of comparisons required to sort the array in the correct order. According to the formula, if n is the total number of elements in an array, then the total number of comparisons needed to sort the entire array can be calculated by a simple formula shown on my screen. That is, n is equals to n minus 1. So in this scenario, we need 5 minus 1, that is 4 comparisons or passes to sort the entire array. In the first pass, there are 4 steps. Let us select the first 2 elements, that is 3 and 8. According to the requirement, we need to sort this array in the ascending order. Hence, when we compare 3 and 8, clearly we get 3 as the least number, so we do not need to swap them. Next is the step 2. Comparing the second and third elements, which are 8 and 4. Here, we need to swap these 2 elements because 8 is always greater than 4 and it requires placing the elements in the ascending order. Now moving ahead, we have step 3. Moving on to the third and fourth elements, which are 8 and 2, And here again we need to swap 8 with 2 because 8 is greater than 2. And in the step 4, we have the last elements which are 8 and 12. There is no need to swap because 8 is already less than 12, so you can see it clearly. So now we enter into pass 2, and in pass 2 we need 3 steps. So the first step, in the second pass, let us select the first 2 elements which are 3 and 4. No swapping is necessary as they are already in order. Next we have step 2. In step 2, we need to select the elements 2 and 4. As you can see, 2 is always less than 4, so there is no swapping required. Next we have step 3. In step 3, we need to compare the elements 4 and 8. And here, we may not need any switching because 4 is already less than 8. Now here you can see that we are not comparing 8 and 12 because the last element is already sorted. Now, we have come to the last pass. And here, there is only one step. The step is to compare the first 2 elements, 2 and 3, and then swap them as 3 is greater than 2. Now, the array is finally sorted and we do not need to do any more comparisons. After understanding the working process of the bubble sort algorithm, we will see its pseudocode. In this pseudocode, there is a function named as bubble sort. The bubble sort function includes an array of collections of sortable elements. Let us consider n as the length of the array. After that, we have to repeat comparisons for the first element to the last element of the array. If the first element is greater than its next consecutive element, then we must swap both the elements and place them correctly. We do not need to switch after closing this repeated statement and getting out of the loop. This bubble sort function will end. After understanding the pseudocode of the bubble sort algorithm, let's learn about the optimized bubble sort algorithm. So we can optimize the algorithm's inner loop by programming it to avoid the comparison at n-1 position after every iteration, since the nth element is already sorted in the previous iteration. More generally, more than one element may be placed in their final position on a single pass. All the elements after the last swap are sorted in every pass and do not need to be rechecked. Optimized bubble sort algorithm allows skipping over many elements. This results in a worst case, that is 50% improvement in comparison count, and adds little complexity because of the new code subsums the swapped variable. Next, we will learn variations of the bubble sort algorithm. So, there are 2 variations of the bubble sort algorithm. They are odd even sort and cocktail shaker. So, odd even sort is a parallel version of bubble sort for the message passing system, whereas cocktail shaker is a sort of bidirectional bubble sort that first goes from beginning to the end and ends to the beginning. After knowing the variation of the bubble sort algorithm, now we will see the complexity of bubble sort algorithm. So the best case of the bubble sort algorithm is big O of n, where n is the number of elements being sorted, and worst and average cases of the bubble sort algorithm are big O of n into n, and lastly, the space complexity of the bubble sort algorithm is big of 1. Here, n is the number of data elements being sorted. Let us understand when this complexity occurs, the best case of bubble sort algorithm is O of n, which occurs at all the data elements in an array are already sorted. Here we have an example with some data elements in an array which are already sorted, that is 10, 20, 30, 40 and 50. Next, talking about the average and worst case, the worst case and average case of the bubble sort algorithm is O of n to the power 2, that is n squared or n into n. It occurs when all the data elements in an array are reversely sorted. Again, we have an example that consists of data elements that are reversely sorted, that are 50, 40, 30, 20 and 10 in an array. Lastly, we have space complexity. The space complexity of bubble sort algorithm is O of 1 because only one additional variable is required to implement bubble sort algorithm, that is temporary variable. We came to the last topic where we will understand 4 main applications of bubble sort algorithm. First application of bubble sort algorithm states that this sorting technique is used to sort the elements in a specific order. The bubble sort algorithm uses less storage and is the second application of bubble sort algorithm. Third, the real-life application states that the bubble sort algorithm is used to sort the students based on their height in a line. Lastly, bubble sort is used to create a stack, pile up the elements based on their height. After covering all the bubble sort algorithm topics, we will now see a practical demonstration of bubble sort algorithm. Now, on my screen, we have an example for bubble sort algorithm. So, let us get started with the code. In this code, at the first position, we have some header files, that is standard input, output, standard library, etc. After that, we will define the main function. In the main function, we will declare an array with maximum size of 50. So here, you can see that we have the first array variable that size is 50. Size will be defined with declaration only because we cannot change the array size in the runtime. After that, we will declare 4 variables, that is a, b, num and temp. Num variable will store the number of elements of an array. After that, we will ask the user how many elements are required for the array using printf function. So here is the printf function where we will be asking the user to enter the number of elements in an array. And the user will enter the elements, and this will be done using scanf function. Then finally, we will print all the elements that the user wants to store in an array using another printf function. We will have 3 loops. Firstly, there will be a loop from the first element to the last element of the array. So this is the first for loop we need. Then second, the for loop will use the variable a for the rotation purpose. As we know, rotation equal to number of elements minus 1. So it will make a loop from index 0 to number minus 1. The last loop is used for how many passes will be required for the implementation. And we already pass equally to the number of elements minus number of rotations minus 1. So there is the loop from index 0 to number minus a minus 1. Then there will be the if condition, stating that if the first element of an array at index b is greater than the element at the index b plus 1, then we will make swap. Then we will come out of the loop and we will print all the array elements after performing the bubble sort algorithm. Now, let's quickly execute this program and see the output. So you can see the program got successfully executed. Now, let us enter the number of elements. Let me choose 5. Now, let us enter the elements in a random order. So this was the array input 3, 2, 4, 1 and 5, and here after executing the bubble sort algorithm, we have the sorted array, that is 1, 2, 3, 4 and 5.
Let's get started with an introduction to quicksort. A quicksort is a highly efficient sorting algorithm, and it is based on partitioning an array into smaller subarrays, and then we will sort these two resulting subarrays in the same manner. This algorithm is quite efficient for large size data sets, as its average and worst case complexities are big O of n square. Now let's discuss algorithm of quicksort. Let's say we have an array. First, we have to select a pivot. We can select either the first element or the last or medium or any random element as pivots. This pivot will dissect the array into two subarrays. Then we will shift all smaller elements than the pivot element to the left. Then we will again apply the same operation for the left subarray and take pivot like we did for the main array. We will perform the same for the right subarray as well. We have now introduced the quicksort and its algorithm. Now let's implement this algorithm in the code editor. We will start by creating a function swap. So void swap int star x comma int star y int temp is equals to star x is equals to star y ry is equals to temp. Now we will write a function which will partition this array. This function will take the last element as pivot and the pivot element at its correct position in sorted array and places all smaller elements to the left of the pivot and all greater elements to the right of the pivot. So int partition int arr comma int low comma int high. So int pivot equals to arr high. Now int I is equals to low minus 1. So for int j is equals to low, j less than equals to high minus 1, a plus plus. Now if current element is smaller than the pivot, so if arr at j is less than pivot, then we will increment the I. Then we will swap ampersand array at I comma ampersand array at j. Then we will swap ampersand array at I plus 1 comma ampersand array at high. And then we will return I plus 1. Now we will write the main function that implements quicksort. So void quicksort int arr bracket comma int low comma int high. So if low is less than high, int pi is equals to partition arr comma low comma high. Now we will separately sort elements before partition and after partition. So quicksort arr comma low comma pi minus 1 and quicksort arr comma pi plus 1 comma high. Now we will write a function to print this array. So void print array int arr comma int size int I. So for loop I is equals to 0, I less than size I plus plus cout array at I cout and L. Now we will write the main block. So int array and comma 7 comma 8. Now we will find the size. So int n is equals to size of array is divided by size of array element at 0. Now we will call quicksort for array comma 0 comma n minus 1. Now we will print this. So cout sorted array now print array arr comma n. Now let's execute this. As you can see, we have successfully sorted our array. Let's get started with introduction to binary search tree. Binary search tree is a set of nodes organized in such a manner that they all have the same binary search tree characteristics. A key and a value is assigned to each node. The requested key is compared to the keys in binary search tree. So during search, if the key is found, then the corresponding value will be retrieved. Next up, properties of binary search tree. First up, the left subtree of a node contains only nodes with keys lesser than the parent node. Next up, the right subtree of a node contains only nodes that are greater than the parent node. The left and the right subtree each must also be a binary search tree. Next, let's discuss what are the operations we can perform on a binary search tree. First up, insertion. Last, deletion. Let's discuss them in detail. First up, insertion. We can insert a node in such a way so that we obey binary search tree rules. That is, the new node should be either less than the parent node if it's on the left subtree, or if it's on the right subtree, it should be greater than the parent node. Let's execute this in the code editor. We will start by creating a class for the binary search tree. So class bst int data and bst pointers left, comma, right. Next, we will define some functions publicly. Public first default constructor and a parameterized constructor. A function to insert the value. And a function to traverse the node. Now let's write default constructors definition. So bst. Now let's write the parameterized constructors definition. Bst int value data is equals to value and left is equals to null and right equals to null. Now let's write the definition for the insert function. So bst insert bst star root comma int value. Now we will check if the tree is empty or not. So if root, then we will insert the first node. So we will return new bst value. Otherwise we will insert the data. So if the value is greater than root data, then we have to insert it in the right subtree. So root right is equals to insert root right. comma value. Else the value should be inserted in the left side. So root left is equals to insert root left comma value, and then we will return root. Now let's write the traverse function. So void tst traverse tst star root. If root then we will return, otherwise we will first traverse left side, then we will print the root data. And then we will traverse the right side root right. Now let's write the main block. So we will start with an empty tree. So bst b comma star root is equals to null. The root is equals to b dot insert root comma 50. B dot insert equals to root comma 10. B dot insert gonna be root comma 30. B dot insert gonna be root comma 50. Sorry, we already used 50, so we will use 60. B dot insert root comma, let's use 20. Let's try to traverse this. So B dot traverse root. Let's execute this. As you can see, we have successfully created and traversed our first binary search tree. Let's get back to slides.
At last, deletion. We will delete a node following the binary search tree rules. That is, the value of the left subtree should be less than the parent node, and the value of the right subtree should be greater than the parent node. Let's try these in the code editor.
Let's start by creating a node. This time we will use structure. So struct node int key struct node star left comma star right. Now we will create a utility function to create a new binary search tree node. So struct node star new node int item. Struct node star temp equals to struct node star malloc size of struct node. Next, temp will be assigned the key is equals to item. Temp left equals to null and temp right is equals to null. Now let's write a function to traverse the tree. Traverse struct node star root. So if root is equals to null, so traverse root left cout root e traverse root right. Now let's write a utility function to insert the new node with the given key in the binary search tree. So struct node star insert struct node star node comma int key. So if node is equals to null, then we will return new node key. Otherwise, we will recur down the tree. So if key is less than the node key, Then we will insert in the left subtree. So node left is equals to insert node left comma key. Else node right should be inserting key. Now let's return the node. Now we have given a non-empty binary search tree, so we have to return the node with the minimum key value found in that tree. So we will start struct node star min value node struct node star node struct node star current is equals to node. So we will loop down to find the leftmost leaf. So while current and currents left is not equals to null, so current should be equals to current to return current. Struct node star delete node struct node star root comma int key. If root equals to null, return root. Now if the key to be deleted is smaller than the root's key, then it lies in the left subtree. So we will check if key less than root key, then root left, it will be equals to delete node root left key. Comma key. Now if the key is deleted is greater than the roots key, then it lies in the right subtree. So else if key is greater than root, root right is equals to delete node root right comma key. Else if roots dot left equals to null and root dot right is equals to null, then return null. Else if root left equals to null, then struct node star temp is equals to root right and free root return temp. Else if roots right is equals to null, then struct node star temp is equals to root free root return temp. Now node with the two children get the in-order successor. smallest in the right subtree. So struct node star temp is equals to min value node root right. Now we will copy the in-order successors content to this node. So root is equals to temp. Now we will delete the in-order successor. So root right equals to delete node root right comma temp t. Now we will return root. Now let's write the main block. We will start with an empty tree. Struct node star root is equals to null. Now root is equals to insert root comma 2 root is equals to insert root comma 5 root is equals to insert root comma 3 root is equals to insert root comma 4 root is equals to insert root comma 7 and root equals to insert root comma 6. Let's try to traverse this. So see out traversal of the given tree. Traverse root. Now first we will delete a value. So see out delete 2 now root is equals to delete node root comma 2 or cout traversal after deleting the traverse route. Let's execute this. As you can see, we have successfully deleted 2 and traversed the tree again. Let's get started with an introduction to insertion sort. Insertion sort is basically a sorting algorithm in which each item in the final sorted array is sorted one at a time. And it is significantly less efficient than more sophisticated algorithms like quicksort, heap sort, or merge sort on larger datasets. Now, let's discuss the algorithm of insertion sort. Let's say we have an array. We will start with traversing the array from index 1 to n-1. While traversing, we will compare elements at the current index to its predecessor. If the data at the current index is smaller than its predecessor, then we will compare it with the element before that. After that, we will shift bigger elements to an index up to make space for swapped elements. Then we will shift the bigger elements to an index up to make space for the swapped element, and then we will iterate the same steps again to sort the complete array. We have now introduced the insertion sort and its algorithm. Now let's implement this algorithm in the code editor. We will start with creating a function to sort an array using insertion sort. So void insertion sort we will give it argument as int array arr comma int size. We will declare variables int I comma key comma j. Now we will create a loop for loop from I is equals to 1 to I less than size I plus plus. Here we are traversing this array from index 1 to the size n minus 1. So key is equals to arr at I and j is equals to I minus 1. Now we will move the elements of arr 0 to I minus 1 that are greater than the key to one position ahead of the current position. So while j is greater than equals to 0 and arr at j is greater than key, then we will swap these. So arr at j plus 1 is equals to arr at j, and j will be equals to j minus 1. And then we will assign arr j plus 1 is equals to key. Now we will write a function to print this array of size void print array we will give its argument as int array and size. We will declare int I is equals to 0. For loop I is equals to 0, I less than size, I plus plus, cout arr bracket I and cout handle. Now we will write the main block. So int arr is equals to 12, 11, 15, 9, 6, 7. And size is equals to, we will find the size using size of, so size is equals to size of arr divided by size of arr at index 0. Now we will print this array without sorting. So cout unsorted array and we will print array arr size. Now we will call insertion sort arr size. Cout, we will print this array sorted now we will again call print array argument as arr size. Now let's print this. As you can see, our function is working flawlessly. It has sorted this array.
Now let us try to understand what exactly is searching. Searching in data structure refers to the process of finding the desired element in the set of items. The selected item is called the target element. Any data structure such as an array, linked list, tree, or graph can be used for searching a set of elements. In data structures, searching can be categorized into two types. First type is the sequential search, in which we check the elements in a data list or an array one by one. In data structures, searching can be categorized into two ways. The first type is a sequential search, in which we check the elements in a data list or an array one by one. An example for sequential search is linear search. Now, let us learn about the next type of searching approach. The next type of searching approach is the interval search approach. Interval search divides the search in half by repeatedly targeting the center of the dataset. The binary search algorithm can be an example for interval search. We will go over the binary search algorithm in detail in our upcoming video. After understanding the logic of search and the types of search, we will get into understanding what is linear search algorithm. The linear search method is a simple search technique. In this type of searching approach, we perform a sequential search across all objects one after the other. Every element is examined, and if there is a match found, then the specific element is returned. Otherwise, the search will continue until the data gathering is complete. Let us go through an example for better learning experience. On my screen, we have the following elements: 50, 10, 20, 30, 70, 40, 90, 60 as randomly distributed elements. Let us imagine that our target element is 70. We found that our target element was 70 using linear search strategy. So, how does it work? In the next segment, we will look into the working terms of linear search algorithm. The simplest method of searching the data collection is the linear search. Starting from the beginning of the dataset, each element is examined until no match is found. The linear search is completed after the item has located. In the first stage, we compare the first element, that is 50, to the searched element, that is 70. We will go on to the next element because 50 and 70 are not matched. We will compare the second element, which is 10, to the search element, that is 70, in the next step. And once more there is no match found. Then we have the element 30 as the next comparison, and 70 and 30 are not matched. We have the next element, that is 20, in the fourth phase, and there is no match when we compare 20 with 70. Moving on to the following stage, we have the data element 70, and after comparing 70 with the search element, there is a match. We will now have the searching and display index as 4, and this index contains the searched element. We now comprehend the pseudocode of the linear search algorithm after learning the working terminology of linear search algorithm. First, we have a function called linear search which has two variables in its parameters, the array's name, which is an array, and the search variable, which is the value. Then, using a for loop, we must search for our target variable by analyzing all the data elements in the dataset with the condition that is the searched item is identical to any set's value. We must return its index value. Now we must stop searching once the searched value has been discovered. Then we will close our if and for loop as well as the linear search function. We will now look into the complexity of linear search algorithm after comprehending the pseudocode. The complexity of linear search algorithm is divided into three categories: the best case, which is the big O of 1, the average case, which is the big O of capital N, and the worst case scenario, which is same as the average case, which is the big O of N. Here, N is the number of data items to be sorted. Let us look into how all these complexities of linear search algorithm play out in detail. First, we have the best case, which is big O of N. As a result, the best case scenario happens when the searched element is found in the dataset's first block. As a result, the search takes a constant amount of time. Here is an example of an array with 50, 10, 40, 20, 30 as the elements. Now, our search element is 50, which is located in the first location of the array. Then, there's the typical case of linear search algorithm, which has big O of N and occurs when the search element is in the middle of the dataset or any point of the dataset. With the array containing the same search element 50, we can easily see that the element 50 is present in the center of the array at the location number 2. Finally, we have the worst case, which is big O of N, which is same as that of the average case of the linear search algorithm and happens when the search element is in the last block of the dataset. As a result of the number of searches required is proportional to the number of elements. As demonstrated in this example, the searched element 50 is found in the last block of the array index, which is 4. In the next segment, we will look into some real-world instances of linear search algorithms. According to the first application of the linear search algorithm, linear search is particularly efficient when it comes to discovering a particular string. Next, we will look into the second application of linear search algorithm. When a data set has only few elements, linear search is the simplest to implement. The final real-world application of the linear search algorithm is with the help of telephone directory. You may find out the name of a person with the phone number 123. This can be implemented easily using linear search algorithm. Now, let us have a look at the linear search algorithm working in practical demonstration. So on my screen, we have an example for linear search algorithm. We have included 3 libraries: standard input output, standard library, and console input output library. Then we have entered the main function where we have declared an array with maximum size of 50 elements, a counter variable I, a variable named target where we would store our searched element, and finally num variable where the number of elements in the array is recorded. Then we have a printf function to ask the user how many items are there in the array, and then we use a scanf function to allow input from the keyboard. So we have added %d format specifier to the scanf function, which is used for numeric values and num variable. Then using a for loop, we will try to print all the items in the array starting with 0 and ending with num variable, which is the last element. Then we will enter our search element, which we want to find among all the elements of the array. And as previously said, we'll store the found element in the target variable. Following that, we will use the for loop to examine all the elements in the array. Then we use the if statement to check for the element is identical to our searched element or not. If the element is found, we exit the for loop and we will break the keyword. And if the target value's location is less than the number of elements in the array, then we will return the location. Otherwise, if the value location is greater than the number of elements in the array, then the search will be unsuccessful and we won't be able to find the searched element. Now we will compile this code and see the output. So there you go, the code got successfully compiled. Now it is asking for the number of elements in the array. Let me give us 5 elements. Now let us enter the elements into the array. Let us enter some random elements. Now we have entered the 5 elements. Let me provide the searched element as 2. Now we have found the target element to be found in the location 2. That is 0, 1 and 2. Yeah, 2 is located in the second index location. First, we'll build a breadth first search algorithm which begins by traversing the root node and then moves on to all the other nearby nodes. The breadth first search approach repeats the procedure for all the nodes until the desired node is found. The Q data structure is the data structure that is used for breadth first search algorithm. For a better understanding, we look at an example of breadth first search algorithm. The blue color indicates that the node has been already explored, while the pink color indicates that the node has not been explored yet or visited yet. Next, we'll have our output. We will use a Q data structure to keep track of all the nodes visited and all the nodes that are unvisited. So, to begin, let's look at the algorithm. As a result, we'll have node A, which is added to the output and marked as visited. We must verify all the unvisited adjacent nodes of A, that is node B and node C, and add B and C nodes to the output and NQ to the queue according to the breadth first search algorithm. Then we'll look at any node between B and C. We'll start with node B. Node D is unvisited, adjacent to node B, so we'll add node D to the output and queue. And since node B is now being visited, we'll dequeue it. When it goes to node D, the next unvisited node is node E. Add node E to the output and NQ to the DQ. Once node D has completed its traversal, DQ from the queue. Now, in the case of node E, the adjacent node is node C, which is already visited. Thus, we will DQ node C from the queue. Now that the pointer is pointing to node C and node F is the next unvisited node after the node C, we will set node F to output and queue. Here, the pointer leads to node F, which has no unvisited adjacent nodes. So, we will DQ F from the queue and queue is empty. So, we'll come to the halt here. Here's what we got. That is A, B, C, D, E and F. After understanding all the theoretical aspects of BFS algorithm, let's look at the code of BFS algorithm in C programming language. Now we are on the practical mode. On my screen you can see an example for BFS algorithm. We have declared a two-dimensional array with maximum row and column size of 10 and two arrays. The first one is a square of a maximum size of 10 and the second one, which is a visited, that stores the maximum size of 10 as well. Some variables n, I, j, and finally we declared front, which is initialized with 0, and rear variables, which is initialized with -1. We perform a loop from index 1 to the size of an array visited in this function, with the condition that if two-dimensional array of column 1 and visited array of index is not 1, we initialize variable I to the front of the queue. Then 1 is set as the front of the queue index of the visited array, and we use the breadth first search function with the vertex as the front of the queue until front is less than or equal to rear. Then we enter the main function, where we define the variable x that stores the graph's vertex, and then we use the printf function to enter the number of vertex that will be stored in variable n. Then we perform a loop from index 1 to queue size and visited array, in which we initialize 0 to the queue and index 1 to the visited array. Then after that, we'll enter the graph value in the form of matrix of two-dimensional array by performing a loop with two variables, I for the graph row and j for the graph column. Then we print the source node, which is saved in the variable x. Then we print the source node, which is saved in the variable x, and we call the breadth first search function or method, which takes a vertex x as parameter, and we print which nodes are reachable by looping from index 1 to the size of the visited array. If index 1 of the array is visited, otherwise breadth first search is not possible. So this was the explanation of the program. Now let's try to execute and see the output. There you go. The program got successfully compiled and now it's asking for the input. Now it is asking for the number of vertices. Let's enter the number of vertices as 3. Now it is asking for us to enter the input in the form of matrix. So the first row will be 1, 2, and 3. So these are the first rows. The next rows will be 2, 3, and 4. So the last row elements are 3, 4, and 5. So we have successfully given all the 3 rows of elements. Now let us select the source node. So the source node would be 2. Now all the nodes that are reachable from the source node 2 are 1, 2, and 3. So there you go. That's how you implement the breadth first search algorithm. Now let's get started with the introduction to depth first search. So what is a depth first search? So basically, a depth first search is an algorithm for traversing or searching the tree or graph data structures. The algorithm starts at the root node, selecting some arbitrary node as the root node in case of graph, and explores as far as possible along each branch before backtracking. So DFS starts with the initial node of the graph, then goes deeper until it finds the goal nodes or the leaf nodes or the nodes that have no children. That is the end part. Here you can see 4 and 7 are the leaf nodes. So the depth first search algorithm runs till the end of all the nodes. That is 8, 10. All these are the leaf nodes or the last goal nodes. In DFS, the backtracking starts once all the nodes are explored. And the DFS algorithm uses stack data structure for its traversal. Now that was a brief introduction to the DFS algorithm. Now for a better understanding, let's go through a practical example. So here we have a graph data structure with elements A, B, C, D, E, and F. So we will be running the DFS algorithm and we will be traversing through all the nodes of this particular graph. And the traversal will be recorded using a stack data structure. And we have 2 different colors which will be used to indicate the element's color. So the black color is for the nodes which are not visited yet, and the blue color will indicate the nodes which are being traversed already. Now this is the stack data structure that we will be using for the traversal, and we have another part which declares or which gives out the output of the traversal of the nodes of this particular graph. Now we will begin with the first one, that is A. Now followed by that we will move ahead to B. Then after B we will go through D. Then after D we have E. Next we have C, and last we have F. So that's how we traverse through the graph using the DFS algorithm. Now for a little more understanding, let's go through a practical example where we will be executing a program for implementing the DFS algorithm. So this particular program on my screen is an example for DFS algorithm. So here we have the structure node. So followed by that we have also the methods which will create the edge and which will also print the graph elements. And finally we have the main class. Now don't worry about the code. This particular code segment or the complete code document will be added in the description box below, and you can have access to it and try to run it on your local system and have a better learning experience. Now without further ado, let's try to run this program and get the output and see how the DFS algorithm gets implemented and traverses through the graph. There you go. The program got successfully executed and we had the graph elements, that is 0, 1 and 2 and 3. So it has visited all the elements, that is 2, 3, 1 and 0 according to the stack data structure, and we have found the output over here. What exactly is a bucket sort algorithm? So the bucket sort algorithm divides the unsorted array into several groups known as buckets. So each bucket is sorted using any suitable sorting algorithm or recursively applying the same bucket sort algorithm. I know it's a little complicated to understand, so let's go through an example. So on my screen we have an example of an array consisting of numerical elements, that is 12, 6, 37, 29, 11, 35, 21 and 22. Now we will create some buckets with different ranges. So here we have different buckets ranging from 0 to 7, 8 to 15, 16 to 23, 24 to 31, and finally the last bucket with range 32 to 39. So 6 will be stored in the first bucket, followed by that 11 and 12 will be stored in the second bucket, followed by that we have 21 and 22 stored in the third bucket, followed by that we have 29 in the fourth bucket, and finally the last two elements, which are 37 and 35, stored in the last bucket. In the next stage, all the elements are sorted according to an order that might be ascending or descending. In our case, we have the ascending order. So the final result will be 6, 11, 12, 21, 22, 29, 35 and 37. So this is how the bucket sort algorithm works in real time. Now the next topic, that is working off a bucket sort algorithm in a detailed way. So now we know the briefing of a bucket sort algorithm. Now let's learn the working of bucket sort algorithm in depth. Suppose we have an array consisting of decimal values or floating values as the input. So the first element is 0.47, next we have 0.39, 0.23, 0.55, 0.29, 0.41, 0.59 and finally 0.31. Then we will create an array of size 10 and store 0 in each block. And each block of an array is used as a bucket for sorting the elements. Next we have step 2. Insert the elements into buckets from the array, and all elements are inserted as per the range of the bucket. Buckets ranging from 0 to 1, 1 to 2, 2 to 3, up to n-1 to n. Here, n is the number of elements in an array. So, for our example, 0.23 will be multiplied by 10, which is the size of an array, and that gives us 2.3, approximately equal to 2. So finally, we will insert 0.23 into the bucket number 2. In exact, we will insert other elements into other respective buckets. Followed by that, we have step 3. Elements of each bucket are sorted using the stable sorting algorithms. And finally, the step 4. In step 4, all the sorted elements of each bucket will be gathered and represented in the form of an array. As pseudocode is an informal programming description that does not require any strict programming language syntax, similarly, we will understand it effortlessly. So, in the pseudocode, first we will create n empty buckets. Next, we will insert all the array elements into buckets by multiplying the size of an array We have to keep doing this for every array element as we understood this in working of the bucket sort algorithm. After that, we have to sort individual buckets using insertion sort, and finally, we will concatenate all the sorted buckets. Next, we will learn about the complexities of bucket sort algorithm. First, we will see about time complexity. So talking about the time complexity, we usually have three cases to summarize the time complexity. So first we have the best case. So that the best case is O of n plus k. Next we have the average case, that is O of n into n. And finally we have the worst case, that is O of n. Here n is the total number of elements to be sorted and k is the number of buckets. So let us understand all the three cases one by one. So first we have the best case. So the best case occurs when all the elements are uniformly distributed in the bucket with an equal number of elements in each bucket. If insertion sort is used to sort the bucket sort algorithm, then overall time complexity is O of n plus k. O of n complexity is for making the buckets and O of k complexity is for sorting all the elements. After understanding the best case, now we will see how the worst case occurs in the bucket sort algorithm. The worst case occurs when there are elements of close range in the array. They are likely to be placed in the same bucket. It makes the complexity depend on the sorting algorithm used to sort the elements of the buckets. Complexity becomes worse when all the elements are in reverse order, and if insertion sort is used for sorting, then time complexity becomes O of n into n. And lastly, we will learn how the average case occurs in a bucket sort algorithm. The average case occurs when the elements are randomly distributed in the array. It occurs even when the elements are distributed in uniform way. Bucket sorts run at the linear time. The average case holds true until the sum of bucket sort sizes is linear and in the total number of elements. Next, we will see about the space complexity. So the space complexity of all the bucket sort algorithms is O of n plus k. Lastly, we have stability. So talking about stability, so yes, the bucket sort algorithm is stable. After understanding the complexity of bucket sort algorithm, now we will compare the bucket sort algorithm with other algorithms. So first, we will compare the counting sort algorithm. Bucket sort can be worked as a generalization of counting sort algorithm. And if each bucket has size 1, then the bucket sort degenerates to counting 0. The variable size of bucket sort algorithm allows it to use O of n memory instead of O of m memory, where m stands for the distinct value that gives counting sort O of n plus 1 worst case behavior. Next, we will compare the bucket sort algorithm with quicksort. Bucket sort with two buckets is a practical version of the quicksort, where the pivot value always selects the median value of the value range. Another meaning of choosing the pivot in quicksort, such as a randomly selected pivot, makes it more resistant to clustering it in the input distribution. After that, we have the merge sort. The n-way merge sort algorithm starts by distributing the list into n sublists and sorting each one. Then, the sublists created by merge sort have overlapping ranges and cannot be recombined by a simple concatenation bucket sort. Lastly, we have one more sorting algorithm, that is Radix sort for comparison. Top-down Radix sort can be a particular case of bucket sort where both range of values and the number of buckets has contained the power of 2. This approach can accelerate the scatter phase since we only need to examine each element's prefix of bit representation to determine a bucket. At last, we have one more topic to learn, that is the applications of bucket sort algorithm. The bucket sort algorithm consists of two main applications. First, by using bucket sort algorithm, input is uniformly distributed on the range. And second, by using bucket sort algorithm, there are floating point values. Now, let us go through a practical demonstration of bucket sort algorithm. Now, on my screen, we have an example for bucket sort algorithm. So we will begin with the header files. Followed by that, we will define a function, namely bucket sort algo. This particular function is to implement a bucket sort algorithm. In the function's argument, there will be an array, namely arr, and a variable num, which will store the number of elements in an array. After that, we will define two counter variables, which are I and j, and declare one more array, namely array1, with the same size of an ARR array. So this particular second array will be used for displaying all the elements in the array1. We will have a for loop which will run from index 0 to the entire size of an array, and for this array, we will use the variable I as the counter variable. We will have another for loop to print all the repeated numbers with frequency in an array. We will run another for loop from index 0 to the last element of both the arrays, and elements of array and array1 will assign to ARR array. Now we will exit from both the loops, and now we will enter into the main function where we will declare an array, namely array, with the size of 100 and two variables which are num and I. Next, we will ask the user to enter several elements of an array using printf function, and now the user will enter number of elements and we will scan that using the scanf function. Now we will ask the user to enter the elements of an array using printf function, and the entered elements will be scanned using the scanf function. And next, we will print a before sorting and an array after sorting using for loops by calling the bucket.algo function, and in this function we will pass the name of an array, that is an array, and the size of an array, that is num. Now let us try to execute this program and see the output. So there you go, the program got successfully executed. Now let us try to enter the number of elements, that is 5. Now let us enter all the 5 elements, 2, 3, 1, 4 and 5. So the array before sorting was 2, 3, 1 and 4, 5. Then the array got sorted using bucket sort algorithm, and the resultant array is 1, 2, 3, 4 and 5 in ascending order.
Let's get started with an introduction to counting sort. Counting sort is a sorting algorithm that sorts the elements of an array by counting the number of occurrence of each unique element in the array. The count is stored in an auxiliary array, and the sorting is done by mapping the count as an index of that auxiliary array. Now let's discuss the counting sort algorithm. Let's say we have an array. First, we will find the largest element in this array to evaluate the range of the elements. Then we will create a count array to store the count of element from the array. Then we will update the count array's element with a cumulative count. At last, we will output each element from the array followed by decreasing its count by 1. We have now introduced the counting sort and its algorithm. Now let's try to implement this algorithm in the code editor. Let's start by creating a count sort function. Void count sort. Its argument as int arr, comma int n. We will declare an array output with size 10 and an array count again with the size 10 and an integer variable max is equals to arr at 0. Now we will write a for loop to find the largest element of this array. So for int I is equals to 1, I less than n, I plus plus, if arr at I is greater than max, then max will be equals to arr at I. Now we will initialize the count array with all zeros. So for int I is equals to 0 to I less than equals to max plus plus I count at I is equals to 0. Now we will store the count of each element in this array. So for loop int I is equals to 0, I less than n, I plus plus, count at arr bracket I is plus plus. Now we will write a for loop to store the cumulative count of each array. So for int I is equals to 1, where I is less than equals to max, at I plus plus, count at I is equals to plus equals to count at I minus 1. Now we will find the index of each element of the original array in count array and place the elements in the output array. So for int I is equals to n minus 1, I greater than equals to 0, I minus minus. So output a count at arr I minus 1 is equals to arr at I, and then we will decrease count arr I by 1. Now let's write a function to print this array. So void print array. So int arr bracket comma int n. So for loop int I is equals to 0, I less than n, I plus plus, cout arr at I out and L. Now let's write the main block int arr is equals to, we will write the element Now let's find out the size of this array. So int n is equals to size of array divided by size of array's first element. Now we will call the count sort function. Arr comma n. Now we will print this array. So print array arr comma n. Now let's try and execute this. As you can see, we have successfully sorted this array using counting sort. Let's get started with an introduction to Radix sort. Radix sort is a non-comparative sorting algorithm. It avoids comparison by creating and distributing elements into buckets according to their radix. And for elements with more than one significant digit, This bucketing process is repeated for each digit while preserving the ordering of the prior step until all digits have been considered. Now let's discuss Radix sort algorithm. Let's say we have an array. First, we will find the largest element in the array to decide maximum number of significant digits we will need to compare to sort this array. We will go through each significant place and sort the array one by one. First, we will sort the array according to the units place. Then we will sort according to the tens place. And then we will sort according to hundreds place and so on till the array is sorted. We have now introduced the Radix sort and its algorithm. Now let's implement this algorithm in the code editor. We will start with an utility function to get maximum value in this array. So int get max with an argument as array arr, comma size n. We will declare variable int mx is equals to arr at 0, and we will write a for loop where int I is equals to 1 to I less than n at I plus plus if arr at I is greater than mx, then mx will be equals to arr at I, and then we will return the value of mx. Now we will write a function to do counting sort of array arr according to the digits represented by exponent. So void count sort at int arr, comma int n, comma int exp. We will declare an integer array output int I, comma a count array of size 10 where all elements are 0. Now we will store the count of all the elements of the array arr. So for loop I is equals to 0 from I less than n to I plus plus count arr at I divided by exp modulus of 10 plus plus. Now we will change count I so that count I now contain actual position of this digit in output. So for I is equals to 1, I less than 10, I plus plus, count I plus equals to count I minus 1. Now we will build the output array. So for loop at I is equals to n minus 1 to I greater than equals to 0 and I minus minus output count ARR at I divided by exp modulus 10 minus 1 is equals to ARR at I. And now count ARR at I divided by exp modular 10 minus minus. Now we will copy the output array of ARR so that ARR now contains sorted numbers according to the current digit. So for I is equals to 0, I less than n, I plus plus, ARR at I is equals to output at I. Now let's write the main function that will sort the ARR using Radix sort. So void Radix sort int ARR comma int n. Int m is equals to get max ARR comma n. Now we will do the counting sort for every digit. Note that instead of passing digit number, exp is passed. Exp is basically 10 raised to the power I, where I is current digit number. So for int exp is equals to 1 and m divided by exp is greater than 0, while exp is multiplied equals to 10, we will do count sort on ARR of size n with exp. Now let's write a function to print this array. So void print array int ARR comma int n for int I is equals to 0, I less than n, I plus plus, say out array at I. Now let's write the main function. We will declare int arr bracket with values 170, 45, 75, 90, 802, 24, 2, 66. Now we will find out the size of this array arr. N is equals to size of arr divided by size of arr first element. Now we will call the Radix sort function. And we will print this array. Now let's try and execute this. As you can see, we have successfully sorted this array using Radix sort.
Hey everyone, I'm Bebo Khandelwal and I welcome you all to Simplilearn's YouTube channel. In this session, we will discuss heap sort. We shall begin our session by introducing what is a binary heap. Then we will discuss the implementation of the heap sort. After that, we will check out various applications of heap sort. Finally, we will sum up what we have learned from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon below so you never miss an update from Simplilearn. Let's get started with what is a binary heap. It's a complete binary tree with all levels completely filled except the last level, where all leaves are to the left as far as possible. A binary heap can be either min heap or max heap. In a min binary heap, the elements at root must be minimum among all elements present in the binary heap. Max binary heap is like min heap, where root must be maximum among all elements. Now let's discuss implementation of heap sort. First, we will start with creating a max heap of elements present. Next up, we will remove the elements at the root and put it at the end of the array and put the smallest element at the root. After that, we will reduce the height by 1. Finally, we will heapify the root element again and repeat the process from step 2. Now let's try to implement this algorithm in the code editor. We will start by creating a function to heapify a subtree rooted with node I, which is an index in array arr, and n is the size of the heap. So void heapify int arr comma int n comma int I. Now we will initialize largest as root, so int largest is equals to I. Now we will define the left and the right subtree. So int L is equals to 2 into I plus 1 and int R is equals to 2 multiply with I plus 2. Now if the left child is larger than root, then if L is less than n and ARR at L ARR at L is greater than ARR at largest, so the largest will be equals to L. Now if right child is larger than the largest so far, so if R is less than n and ARR at R is greater than ARR at largest, so largest is equals to R. Now if largest is not root, so if largest is not equals to I, so we will swap ARR at I with ARR at largest. And then we will recursively call heapify for the affected subtree. ARR, comma, n, comma, largest. Now we will write the main function to do heap sort. So void heap sort int ARR bracket comma int n. Now we will start by building heap. So for int I is equals to n by 2 minus 1, where I is greater than equals to 0 at I minus minus. We will call heapify for ARR, comma n, comma I. Now we will one by one extract an element from the heap. So for int I is equals to n minus 1, where I is greater than 0 at I minus minus. Now we will move current root to end. So swap ARR at 0 to ARR at I. And we will call max heapify on the reduced heap. So heapify ARR, comma I, comma 0 Now we will write a function to print this array. So void print array int arr comma int n. So for int I is equals to 0, I less than n, plus plus I, we will do cout arr bracket I space and a cout and L. Now let's write the code for the main block. So int arr is equals to t comma 18 comma 12 comma 14 comma 5 comma 6 comma 2. Now we will write a statement to find the size of this array. So int n is equals to size of arr divided by size of the first element of the array, arr 0. Now we will call heap sort function. So heap sort for arr comma n. Now let's print this array. So cout sorted array is print array at arr comma n. Now let's try and execute this program. As you can see, our sorting function is working flawlessly.
Let's get started with what exactly is divide and conquer algorithm. A divide and conquer algorithm iteratively divides a problem into two or more subproblems of the same or relative type until they are simple enough to be solved directly. The subproblem solutions are then integrated to solve the original problem. There are three steps involved in the divide and conquer principle, that is, divide, conquer, and combine. The first step is to divide the significant problem into smaller subproblems. The second phase is to conquer the solutions to all divided subproblems. Then, the final step is to combine and merge all of the solutions to create a definite solution. We will understand this by an example right here on my screen. Suppose we have a large problem. We can use divide and conquer technique to divide it into n number of subproblems such as problem 1, problem 2, problem 3, problem 4 and so on until we reach the problem n. Then we conquer all the solutions to the specified subproblems as solution 1, 2, 3, 4 and so on. And finally, we merge all the solutions to get one definitive solution. Now that was divide and conquer algorithm. Followed by that, let us get into merge sort algorithm. So merge sort is one of the most efficient sorting algorithms. It is based on divide and conquer strategy. Merge sort continuously divides a list into numerous sublists until each sublist contains only one entry. Then merges all those sublists into a sorted list. There are 4 elements on my screen. We have 7 and 3 in the left half and 5 and 2 in the right half. After dividing the 4 elements in half, we combined all the items in ascending order, that is 2, 3, 5 and 7. In the next segment, we are going to understand how it happened and we are going to learn the working procedure of merge sort algorithm. There are 2 approaches to implement the merge sort algorithm. The first method is top-down approach and the second method is bottoms-up approach. The first method, that is the top-down approach, implies that it begins with the large picture. From then, it's broken into smaller chunks. Now the second method, that is the bottom-up technique, which starts with a specific number of jobs and works its way up to the general. Let's have a look at how to implement the merge sort algorithm using top-down approach. The top-down merge sort approach is the methodology that uses a recursion mechanism. It starts at the top and proceeds downwards, splitting the array into 2 halves, making a recursive call and merging the results until one gets to the bottom of the array. For a better understanding of the top-down approach method, consider the following scenario right here on my screen. We have an example of an array of size 6 consisting of elements 7, 3, 9, 5, 6 and 4, starting with 0 and ending with 5. Using the following formula, we'll divide the array by its middle. That is, middle is equals to left plus right divided by 2. We have 3 elements on the left and 3 elements on the right near the middle. So according to the top-down strategy, we divide the given array in half, resulting in 3 elements, that is 7, 3 and 9 on the left and 5, 6 and 4 on the right. Next, we sort all these elements in ascending order. By doing so, the first half will be 3, 7 and 9 and the right half will be 4, 5 and 6. And after merging all of them, we will have the sorted array, that is 3, 4, 5, 6 and 9. Next, we will understand the bottoms-up approach. An iterative process is used in bottoms-up merge sort approach. It starts with a single element array and then joins 2 neighboring items while also sorting them. The combined sorted arrays are combined and sorted again only until one single unit of the sorted array elements remains. Now, let us look at an example right here on my screen. In the first iteration, we will merge pairs of array sizes by 1, sorting each of the 2 elements. When you iterate the array by size 1, the elements 7 and 3 become 3 and 7. Similarly, 9 and 5 become 5 and 9. And finally, 6 and 4 become 4 and 6. We will merge the pairs of array size by 2 in the next iteration with the bottoms-up method. As a result, the elements 3, 7 and 5 will become 3, 5 and 7, and the same way 9, 4 and 6 will become 4, 6 and 9. In the last iteration, merge pairs of array size by 3 so that after sorting 3, 5, 7, 4, 6 and 9 becomes 3, 4, 5, 6 and 7 as sorted arrays. After understanding the working procedure of merge sort algorithm, we will now see the pseudocode of merge sort algorithm. We have a function called merge sort in this pseudocode, and parameter of the function contains an array named as array and 2 variables named as left and right. If the number of elements in the left is greater than the number of elements on the right, we will get a middle using formula left plus right divided by 2. The merge sort is called and this function now has an array, a left variable and right variable. By calling merge sort, we have array left as middle plus 1 and right variable. And finally, by calling merge sort, we have left, middle and right variables. In our upcoming segment, we will implement the merge sort method in a practical demonstration. In the next section, we will discuss the complexity of merge sort algorithm. First, we will look into the time complexity of merge sort algorithm. As we all know, time complexity in data structures is divided into best case, average case and worst case. The best case of merge sort algorithm is big O of n into log n. Average case of merge sort algorithm is big O of n into log n. and the worst case of merge sort algorithm is big O of n into log n. The number of elements being sorted is given by n. Merge sort's time complexity is big O of n star log n in all three situations, that is worst, average and best, because it always divides the array into two halves and merges the two halves in linear time. It takes up the same amount of space as the unsorted array. As a result, it is not a good idea to use it to search big unsorted arrays. Moving on to the space complexity of the merge sort algorithm. The space complexity of the merge sort algorithm is large O of n. In the merge sort algorithm, we store the left and right parts of the merged array in the temporary arrays and then utilize the original array to keep the entire merged array. In the worst case scenario, the left and the right sub arrays will each be n by 2 in size, and then the total auxiliary space will be big O of n, resulting in a space complexity of big O of n. Following that, we will look into several applications of the merge sort algorithm. So the first application is merge sort is an efficient way to sort linked list in big O of n log n time. Subsequent application of the merge sort algorithm is for linked lists. Merge sort implemented without taking up more space. Followed by that, the merge sort method is used to count the number of inversions in a list. Last application states that in internal sorting, the merge sort is employed. Now let us look into some of the drawbacks of merge sort algorithm. So some of the drawbacks of merge sort algorithm are: for smaller assignments, merge sort algorithm is slower than the other sorting algorithms. For temporary array, the merge sort technique requires an additional memory space, that is space of big O of n. Now let us look into a practical demonstration of merge sort algorithm. On my screen we have an example for merge sort algorithm. To define constants or micro substitution, we use the hash define as preprocessor directive with a constant variable max of 10. Following that, two arrays, array1 and array2 are declared. We declare array1 and initialize it with elements like 8, 4, 7, 6, 2, 3, 5, 9, 10, 4 and 1. Array2 is used for temporary array. Then, to implement the merge sort concept, we declare a merge sort function. We specify three variables in this function parameter, that is left, right and middle. The left variable is used to display the left part of the array1, the right variable is used to display the right part of the array1, and middle variable is used to indicate the middle or center of the array in this function. We utilize the for loop in this function, setting the left to level 1, the middle plus 1 to level 2, and the left to variable I with the condition that level 2 is less than or equal to the middle and level 2 should be less than or equal to the right of the array. We have a condition in this for loop that if level 1 of array 1 is less than or equal to level 2 of array 1, we will initialize all the consecutive elements of level 1 of array 1 to array 2. Else, we will initialize all the successive elements of level 2 of array 1 to array 2. Out of for loop, all subsequent elements of level 1 of array 1 will be initialized to array 2 until level 1 is less than or equal to the middle. All successive elements of level 2 of array 1 will be initialized to array 2 until level 2 is less than or equal to the right of the array. Using the loop, which will run from I equal to the left of I is less than or equal to right, we initialize all the items of array 2 to array 1. We have declared one more function in this code, namely sorting. Out of the merging sort function, in which only the left and right variables are defined, we specified the middle function in the sorting function with the condition that if the left is less than the right, the middle will be calculated as left plus right divided by 2. Then we called a sorting function passing left as middle as right, and then another sorting function passing left as middle plus 1 and right. Finally, we use the merge sort function passing left, middle and right to the sorting array 1, otherwise we would return nothing. We entered the main function out of the sorting function where we declared the counter variable I and printed the array before sorting using the printf function in for loop. where I will run from index 0 to the array's maximum size. After that, we invoked sorting method, passing left as 0 index number and right as the array's maximum value. Finally, after doing the merge sort process, we will print the array using the printf function and for loop. We will run from 0 to the array's maximum value. Then we compile the program and run it. Now let's try to quickly execute this program and see the output. So there you go, the program got successfully executed and the list before sorting is 8, 7, 6, 2, 3, 5, 9, 10, 4 and 1. And the list after sorting is 1, 2, 3, 4, 4, 5, 6, 7, 8, 9 and 10.
Let's get started with an introduction to selection sort. The selection sort algorithm is an in-place comparison-based method that divides the list into two halves, with the sorted portion on the left and the unsorted half on the right. Then the smallest element from the unsorted array is chosen and swapped with the leftmost element, and that element is added to the sorted array. Now let's discuss the selection sort algorithm. Let's say we have an array. First, we will divide this array in two subarrays, unsorted array and sorted array. Then, we will divide the minimum element from the unsorted array and swap it with the leftmost element of this unsorted array. After that, we will add it to the unsorted array. We will keep repeating this process until there are no elements left on the unsorted array. We have now introduced selection sort and its algorithm. Now, let's implement this algorithm in the code editor.
We will start by creating a function swap. The argument will be integer pointer x, comma, integer pointer y. We will declare an element temp to store the value of pointer x. Then we will store pointer y's value in x. Then we will store temp's value in y. And that's how we can swap them. Next, we will write the definition of selection sort function. Void selection sort. Its argument will be int array arr, comma, int n. We will declare variables int I, j, and a min underscore idx variable to store the minimum index. Now we will one by one move boundaries of unsorted subarrays. So for loop I is equals to 0, where I is less than n minus 1, I plus plus. We will find the minimum element in this unsorted array. So min underscore idx is equals to I. Now for j is equals to I plus 1, j less than n, j plus plus. If array element at jth location is less than array at the min index, then min idx will be updated with j. Now we will swap the found minimum element with the first element. So we will call swap function with argument as ampersand arr at min idx comma ampersand arr at ith location. Now we will write a function to print this array. So void print array argument as int arr and its size int n. For loop int I is equals to 0, I less than n, I plus plus, out arr at I out and l. Now we will write the code for the main block. So int arr is equals to 4, 2, 1, 8, 3. We will find the size of this array. So int n is equals to size of array arr divided by size of this array's first element. Now we will call selection sort function argument as arr, n. Then we will try to print this. So cout sorted array and we will call the function print array to print this array arr, n. Now let's try and execute this program. As you can see, we have successfully sorted this array using selection sort algorithm.
Let's get started with an introduction to shell sort. Shell sort is a sorting algorithm that is based on insertion sort algorithm, and it is very efficient. When the smaller value is on the far right and must be shifted to the far left, then this method avoids significant shifts as in insertion sort. Now let's discuss the algorithm of shell sort. Let's say we have an array. We will initialize a variable h. This h will represent intervals. Then we will divide this array into h intervals. It will create some subarrays. Then we will apply insertion sort on these subarrays. After that, we will reduce the interval h by 1. Then we will repeat this process recursively until h counts down to 1. We have now introduced shell sort and its algorithm. Now let's try to implement this algorithm in the code editor. First, we will start with a function to sort an array using shell sort. So int shell sort, we will write argument as int arr bracket comma int n. We will start with a big interval, then we will reduce this interval by 1. So for loop int interval equals to n by 2 interval greater than 0 and interval divide equals to 2. Now we will do a gapped insertion sort for this interval. So for int I is equals to interval I is less than n, I plus equals to 1, int temp is equals to arr bracket I. Now we will shift earlier gap sorted element up until the correct location for arr I is found. So int a. So for j is equals to I and j greater than equals to interval and arr bracket j minus interval greater than temp and j minus equals to interval. Now arr at j is equals to arr j minus interval. Now we will put this temp in its correct location. So arr bracket j is equals to temp. Now I will return 0. Now let's write a function to print this array. So void print array int arr comma int n. So for loop int j is equals to 0, j less than n, j plus plus cout arr bracket j. Now we will write the function for the main block. So int arr is equals to 12 comma 34 comma 56 comma 85 comma 2 comma 9 comma 11 comma 5. Now let's find the size for this array. So int n is equals to size of array divided by size of first element of this array. Now cout array before sort of print array arr comma n shell sort arr comma n. Now cout arrays after sorting. We will again print array arr comma n. Now let's try and execute this. As you can see, we have successfully sorted this array.
Here, we will look into the real-life example of greedy algorithm in order to understand it better. This is Alex. He's quite wealthy and intelligent as he works for one of the most reputed IT firms. And this is Alex's best friend Rachel. Rachel is in dire need of $85 right now. However, she needs money in such a quantity that the number of coins is kept to a minimum. So Rachel shared this issue with Alex and asked him for help. Now Alex is thinking about Rachel's issue, which he can easily fix because he has a limitless supply of $50, $20, $10, and $5 coins stashed in various bags. Although this being said, Alex needed to think about the constraint Rachel told him about. He needed to give her money such that the number of coins utilized must be minimal. To do so, Alex began making a list of the various coin combinations in which he could present money to Rachel. However, after a while he became confused due to the vast number of conceivable combinations. So he decided to use his programming ability to solve real-life problems. Alex developed a program that will provide him with the optimal number of coins that he can present to Rachel. This generated program was iterating through the different possibilities to choose the best solution. At each iteration, the program added the coin of the largest value that was not taking Alex past the amount to be paid, which is $85 in this case. For $85, the largest denomination ID can start giving is $50. Now, ID is still short of $35 to reach the amount so that the next largest coin program can take in as $20. But since the program still requires $15 to meet the threshold, the next highest denomination it can accept is $10, followed by $5. The best part about this program was that it allowed Alex to present $85 in just 4 coins, which is fairly incredible. The vital thing to note here is that after each loop, the program makes a greedy choice, providing the coin with the highest potential value. What I mean here by greedy is that locally optimal choice is picked at every step to reach the global optimum solution. Now moving ahead, we will formulate the idea of greedy algorithms. Basically, a greedy algorithm is based on a problem-solving method that involves making locally optimal decisions at each stage in the hopes of achieving a global optimum. That means at each stage we choose a locally optimal value in the hopes of arriving at the optimum possible end result. Furthermore, this algorithm is an optimization technique that can find either minimum optimum result or maximum optimum result. The best part about this algorithm is that it is simple to understand and implement as well. Additionally, the runtime complexity for this algorithm is pretty reasonable. However, the fundamental disadvantage of this strategy is that we only receive the globally optimum value in a small percentage of cases. Having said that, you must be thinking about when to implement this algorithm for solving particular problems, as it does not always produce globally optimum results. Well, let me tell you guys that we have two conditions to judge our problem for implementing greedy algorithms. The first condition is the greedy choice property. This notion states that making locally optimal judgments can lead to the global optimum solution for a given problem. The second condition is about optimal substructure. The problem has an optimal substructure only if an optimal solution to the entire problem comprises the optimal solutions to the subproblems. In simpler words, that means the problem can be split down into multiple subproblems, and the solutions to these subproblems can collectively lead to a solution for the entire problem. If both the above-mentioned properties are satisfied by the problem, then we can create a greedy solution for that particular problem. Moving forward, we will look into the steps for constructing a greedy solution. Finding the substructure or subproblem that can lead us to the final answer is the first step in building a greedy algorithm. Because in this algorithm, we are just trying to operate with local optima to reach the global optimum solution. The second step is about determining the type of solution the given problem can result into. That can be either the largest sum or minimum path. The final step for creating the greedy solution is about creating an iterative process for traversing through local stages and making decisions to reach a globally optimum solution. Now, you might be confused about how we can do that. Well, let's go through an example to understand the approach to implement a greedy solution. The example that we are going to deal with is called the traveling salesman problem, in which a salesman is supposed to reach the destination from a given current location. The representation of cities and paths connecting them is done using graph structure, where each node is considered as a city and edges connecting them as paths, having edge weight as the distance between the two cities. Now, in this case, we are supposed to find the minimum path between two cities. So to do that, we will begin from the current arbitrary position. From this node called as starting location, there are three possible paths, but the path towards city B has less distance. Hence, we will traverse this edge primarily as it is an optimal local route. We have reached city B now, and from this node we have two possible paths, out of which one path directly leads us towards the destination city having distance 20, but the other path leading towards the city F has edge weight value or distance value as 2. Hence, according to the local optimal decision, we will choose the edge connecting cities B and F for traversal. We have reached the city F now. From this node or city, there is only one path leading us to our destination. Hence, we will traverse it. Now we have reached the destination city. The path highlighted in the green shade is the global optimum for this TSP problem. You can verify that by calculating the edge weights for all other possible paths. Since this solution allows us to reach the global optimum by making optimal decisions at the local stage, this strategy to solve the problem will be considered a greedy approach. Now moving ahead, we will look into the demerits of using greedy algorithm. We have learned that the greedy algorithm makes decisions based on local optimum instead of analyzing the broader picture of the whole data. Hence, there is a possibility that the greedy solution might not be the best optimal solution for some problems. For example, consider this traveling salesman problem. In this problem, the highlighted part is a created solution to reach the destination city from the current location using a greedy algorithm. But if you observe this graph, the selected solution is not the global optimal solution for this problem. In contrast, it is the worst generated solution to reach the destination. That is why the greedy algorithm is considered to be prone to correctness issues. Even if the algorithm is correct, proving why it is correct is difficult. Thus, it is deemed to be trickier to solve specific issues. Now we will discuss about applications of greedy algorithms to understand their importance. The first application of a greedy algorithm is its use for constructing minimum spanning trees. The coding approaches that we use to generate MSTs is based on the greedy algorithm. Both Prim's algorithm and Kruskal's algorithm are known as greedy algorithms as they make decisions based on locally optimal decisions. The next application of the greedy algorithm is its use to implement Huffman encoding and decoding algorithms. The Huffman coding technique is a lossless data compression method. The concept is to give variable length codes to input characters, the lengths of which are determined by the frequency of the related characters. The smallest code is assigned to the most frequently occurring character, whereas the largest code is assigned to the least frequently occurring character. This process is carried out by making local optimum decisions. Hence, it is also considered to be a greedy algorithm. The final application of the greedy algorithm is its use for developing solutions to well-known coding problems. Those problems are the activity selection problem, job selection problem, and fractional knapsack problem. All these problems generate solutions by making decisions at each local stage. So the solutions for these problems can be developed quite easily using the greedy approach.
So this was all for today's session. I hope this session was informative and interesting. If you have any queries regarding any of the topics covered in this session, or if you need the code for all the coding algorithms discussed in this particular tutorial, then please feel free to let us know in the comment section below, and our team of experts will be happy to resolve all your queries. Until next time, thank you, stay safe, and keep learning.